Hello, can you guys hear me?
Yes, sir.
Yeah, Naveen, just give us a couple of minutes.
Sure. Okay.
Waiting for it to go online.
Okay.
Naveen, can you come online? Are you on the screen?
I'm here. Can you hear me?
Yeah. Can you switch on your video?
Yeah. 1 second.
Yeah. Perfect. Good morning, everyone, and welcome to our 9th session of our webinar series. I'm Nitesh, Assistant Professor at Meenakshi College of Engineering, School of Architecture. And it gives me immense pleasure in having all of you present for our 9th session. Title of the session is the State of the Art of the AEC Field, Data-Driven Design, Machine Learning, and Robotic Construction. The speaker for our session is our very own alumni, Architect NaveenKumar and Muthumanickam. Before I introduce him, I have a couple of pointers as usual. Make sure that your video and audio is completely turned off during the entire duration of the session. And also, if you have any questions related to our session, please send us your questions as a direct chat message to the organizers. We will take them in the end, and I'm sure Naveen would be more than willing to answer your queries. So the speaker for our session today is Architect Naveen. Gives me immense pleasure in welcoming him back to his alma mater. He's from our very first batch, the 2009 to 14 batch, and it gives us immense pleasure in seeing the first batch doing very well. Especially last week we had Firdos as well presenting to us. Seeing that you guys are flourishing and doing multiple things in life gives us a lot of happiness as well. So Naveen by himself is a PhD candidate in architecture at Penn State University, specializing in using machine learning and autonomous robotic construction technologies to design better and efficient buildings. He was also part of the Penn State team at the finals of the NASA National Aeronautics and Space Administration 3D printed Mars Habitat Centennial Challenge, where the team won the second prize. Naveen worked on the building information modeling and optimization for robotic concrete 3D printing as part of the competition. He's also a concurrent engineering candidate in architectural engineering at Penn State, along with a MS in architectural science and building technology degree from the University of Michigan, Ann Arbor. As I already mentioned, he's originally from Chennai and a very own alumni. He's also worked at architectural practices like Sami Fedora and Associates, Studio Daniel Libeskind, and also worked for Autodesk in the recent past. We welcome you and thank you for accepting the invitation, Naveen. I hand over the session to you.
Sure. So, do you want me to take over?
Yeah. Go on.
Perfect. So first of all, before I share anything as in my screen or anything, thank you so much Actually, I might use several Tamil words in between, so bear with me. I guess most of you can understand Tamil. So, சந்தோஷமா இருக்கு ஆக்சுவலா படிச்ச அதே காலேஜ்ல ப்ரெசென்ட் பண்றதுக்கு. ஸோ thanks especially to Stanley sir, Jalaja ma'am, Professor Nitesh, and Pavitra ma'am for giving this wonderful opportunity. And one special mention, thanks to my friend Gautam, who also happens to be a professor currently at Meenakshi College, because he suggested my name to the organizers, and then that's how it started. So thank you so much, Gautam, and it means a lot. I've been following this panel of webinars, like past presenters and stuff, and I was like thoroughly stunned because like all of them were like ரொம்ப பெரிய ஆளுங்களா இருந்தாங்க. So I'm nowhere near to them. I'm like just in the starting phases of my career, plus I haven't achieved much, but நிறைய ஆசை இருக்கு இந்த மாதிரி அச்சீவ் பண்ணணும் அப்படின்ட்டு. So today the presentation will more be like whatever I've learned after my undergrad from Meenakshi College until this year 2014 I graduated, and until like 2020 whatever I've learned I hope to share it with you guys, so that somewhere someone might get inspired or motivated, and then they get to do much more amount of like greater stuff than what everyone else does. So that's the ultimate motto, and it also helps me keep myself motivated. So thank you so much on that note. So without much ado, let me quickly share my screen. So are you able to see my entire screen, or do you see any presenter view or something of that sort? So if someone can confirm.
It's the entire screen.
Okay, perfect. Let me, yeah. So this is my batch actually, like the first batch of Meenakshi College. So like you can see Firdous who presented last week, you can see me, and you can see a lot of other people. So thanks to this wonderful set of cohorts who have like inspired and motivated, and kind of like, because day-to-day conversations with them helped us focus on our goals and then iterate on our ideas and stuff. So first of all, thanks. And I would like to kind of like just introduce that this is my batch. This is the first batch of like this college. You're probably your super seniors, and yeah. So going into the topic today, what I'll be focusing on, as you know, state of the art of AEC field, I'll be focusing on three things. One is data-driven design, and another brief overview of how machine learning can be leveraged, and then like much more detailed overview of like robotic construction. But I've divided the presentation into like 4 sections. First, I know that like Nitesh gave like a thorough intro of me, but I'm just going to give a reintro, a very brief gist of like how I traveled from 2014 until now, what are all the roles that I've worked in and things like that, so that it kind of like ties into the presentation of why I chose data-driven design as my specialization and why I'm doing whatever I'm doing right now. So that part, and then I'll talk more about why AEC, all three together, architecture, engineering, and construction. I'll basically just talk about like a building like goes through a lot of things, right? From design conception until like we get it constructed, and then we start using a building or living inside a building, and then it gets maintained. For example, we buy a car, we just probably use it for like a couple of years, but a building, we stay in a building for almost like 80 to 100 years or even more than that, right? So what are the various stages, and like how data-driven design kind of like can assist designers in dealing or tackling the problems across these various phases. And finally, we get to see robotic construction as well. So let me quickly introduce. So as Nitesh told, President Nitesh told, I studied at Meenakshi College. I graduated in 2014. Back then I was very much into designing buildings, as in like proper architectural design. But immediately I went to University of Michigan, Ann Arbor. 2014 September I came to the US for my master's degree, which was in architectural science and building technology, where more of my focus was on building physics. So things like structural stability, thermal performance of a building, energy performance of a building, acoustic performance of a building, daylighting analysis, and all these things. So I learned a couple of softwares, as well as like each piece of software is like a calculator, right? It does some calculation and then like gives you a result. So I learned what is happening at the back end of these tools. For example, when you plug in a model into Ecotech, it gives you a daylighting graph, but like how is it color coding? What is the principle behind it? That was my interest during my master's. And during my master's, fortunately, like it was, I don't know like if I deserved it, but like I got an opportunity to work with Daniel Biskeen as a spring intern. It was a very, very brief internship, just probably 1 to 1.5 months, but it was like a very good experience for me. And then after that, I got more interested in, say, like, okay, there are these different tools for designing and modeling and analyzing buildings, and then trying to kind of like, from the various spaces, you use a lot of software. So how do you make these softwares talk to each other so that you can better share information? So I started designing or developing softwares to assist building design. So I took up a full-time job at a lab called University of Michigan 3D Lab, where I worked as a research specialist, and more of my work was developing plugins and softwares for building design. And I slowly got interested in taking forward that software development research into a much more robust domain. So that's when I applied for a PhD, got into Penn State, and started working on this area called data-driven design, which I will eventually tell what exactly is the meaning of the word data-driven design. And during my PhD, because of the hybrid nature of like me being an architect who was trained with like building physics knowledge as well, and having like, I wouldn't call myself like a pro programmer. I'm like, I learned things on the go. So because of this hybrid nature, I got an opportunity to work with Autodesk. So I interned at Autodesk twice, 2018 ஒரு வாட்டி and then 2019 ஒரு வாட்டி பண்ணேன். That was also towards data-driven building design. So if you would have heard of this platform called Revit and Dynamo, I worked with that particular team in developing that tool and then kind of like making it much more usable. And this was like a wonderful moment where through my advisor or my professor at Penn State, I got the opportunity to work with like a wonderful set of team, like 25 or 30 people who participated in this NASA competition, where we were trying to kind of like design a building which would have to be 3D printed in Mars. But all the experiments and like the competition and everything, the venue and everything was on Earth, but like we simulated the conditions of Mars and then try to kind of like leverage it. And my specific role, I played a very, very tiny part. I wouldn't take credit for the entire competition. Because of the wonderful set of team that I had, I was able to kind of like contribute in a very, very specific part. So I contributed on how to use data-driven design to design buildings which can be robotically 3D printed or constructed. So given this gist, let me go into what exactly, I mean, I know that like you guys have read the topic, but I want to just give a brief. So AEC field, whenever we start designing a building, right, we get a design brief from an owner or some person or a team of people who want something to be done with the building. They want the building to function in a particular way or for a particular use case. For example, some big shot might come and say, I want a huge convention center, or I want you to design a nuclear power plant for me, or I want you to design like a residential complex for me. So usually we start with a design brief, and then we come up with like some conceptual design options, and then like iterate on that option, and then start doing preliminary design and so forth and so on. And then once we get to a mature state, we detail that design further. And once we do that, then we come up with like construction management techniques, which is like, okay, like we have the design and how do we get it executed on site and what are all the things that are needed for it. And then comes the construction part. And once it is constructed, even then, like there is a role of architect and structural engineer and other professionals who are involved, which is the operations phase of a building. So same as how every product like a phone or like a car has serviceability, even buildings have serviceability. You need to maintain the building for a long standing period, right? So that's where the operations part comes in. So typically, as in this is not a very bird's eye viewpoint of context. So architecture as a profession is involved in more of the design stages, and we also get involved in the construction and operations phase, but predominantly we are confined to the design stages. And then architects, in addition to engineers, get involved and then collaborate during the detailed design phase. Whereas further, if we go into the construction management and construction phase, we get to collaborate with construction managers and then estimators and then general contractors and then trade contractors and all these people, right to the level of all these laborers. என்ன சொல்றது, சித்தால் கொத்தனார்ல இருந்து எல்லார் கூடயும் collaborate பண்ணி we'll have to work. So we get a lot of information from them as well for the design. So given that there are these multiple stakeholders in every project, architects, structural engineers, estimators, energy specialists, and so forth and so on, there is a ton of these people involved. What happens is, if it is a very simple building, let's say a residential building or so, it's the number of stakeholders who are involved might be a little less complicated. But the moment you start designing buildings like, say, a factory or like an office space or like a skyscraper, then there are multiple systems which get involved in it. For example, it's not just the envelope, it's not just the interior, it's not just the electrical, mechanical, and plumbing systems. There are lots and lots of other systems which come into play. And then, which means there are going to be multiple other stakeholders who enter the project. So in such case, how would you take like a decision? For example, if you want to decide on like what would be the shape of the building, or what would be the configuration of the interior layout, or what would be the mechanical routing way, the decision won't be single-handed. Not just the architect won't take it. Instead, he has to consult with the structural engineer, he has to consult with the electrical engineer, he has to consult with like a lot of different people in order to take these decisions. And so typically what happens is, at such points, let's imagine that like we come up with a very, very small design, like a 2-story building. Right now it has some openings which kind of like bring in some daylight inside. And then if, for example, someone decides that I want the building to have more daylight, as in somehow I want the building to be naturally lit totally. So they increase the amount of windows on the building or so that like a lot of daylighting comes in. But the problem here is that the artificial lighting power consumption, don't take it too technical, just probably I would explain it in a much more simpler way. So whenever you have less amount of daylighting, you use a lot of tube lights and interior lights, right? So your artificial lighting power consumption goes up. And recently, I guess you guys might have read in the news, நம்ம EB bill கூட வந்து சென்னையில ரொம்ப ஜாஸ்தியா வந்துகிட்டு இருக்கு அப்படின்னு சொல்லி இது பண்ணாங்க. So your power consumption goes naturally up when you have limited daylighting, because we as human beings tend to use more amount of light. So design option 1, if you see like the artificial lighting power consumption was high, but design option 2 kind of like has a lesser amount of artificial lighting power consumption, because you have more number of openings, which means it brings in more amount of light. But the problem here is design number 1 has less amount of heat retention, because we all know that greenhouse effect and then all these like light getting converted into heat and then getting retained in the interior spaces. So the more amount of glass, more amount of heat retention. So you try to solve one problem, but you're creating another problem, where in design option 2, even though you have more light, you have more heat generated within the building. And that leads to probably say romba soodana, what will we do? We kind of like use AC, air conditioners or fan and like all these things, right? So your cooling energy kind of like goes up naturally. So onna solve panna try panni, we are like negotiating on another thing, we are creating another problem. So in such situations, what happens is, this is a simple graph. You need not worry about like the numbers in the graph. So just focus on the lines. So on the x-axis, we have artificial lighting power consumption. On the y-axis, we have cooling energy. So in the artificial lighting power consumption, if we try to reduce, the cooling energy goes up. And same way, if we try to reduce it further, the cooling energy goes up. So when we try to reduce one aspect, another aspect kind of like increases, which means we have a problem. So taking a balanced decision when multiple stakeholders are involved is very, very tough. In that case, what happens is, இப்போ நம்ம எக்ஸ்பிளைன் பண்ண அந்த எக்ஸாம்பிள் வந்து இஸ் a very very simple example, just 2 or 3 systems, ஒரு like wall system and then like a glass system and then like you have windows and floor plate, that's it. But in a typical building you have multiple systems, right? If you ever visit like a skyscraper or like a modern day office building, you have like HVAC ducts, you have envelope assemblies, you have structural columns and beams, you have the interior walls and lot of other things. So each of these stakeholder designs each of these part, and then they have their own goal, own set of goals. So for each of those goals, there might be multiple options. For example, there might be one option which is like structurally robust, but there might be another totally different option which might have like the most convenient way to route the MEP systems. And then there might be a totally different option which has like the most energy efficient design. And then there might be another massing option which has the perfect daylighting condition. So you can't build 4 buildings for one project, right? You have to come up with one design. So how will you kind of like arrive at a consensus or like come up with one design option which satisfies all these things? Typically, what we do as architects is when there are multiple components, we tend to use rule of thumbs or heuristics. Based on our past experiences and based on past projects, we tend to take decisions based on rule of thumbs. That works to an extent, but when the project complexity goes up, certain decisions that you might take early at the stage might lead to complicated revisions at later stages, which means ஒரு கோடி ரூபாயில பண்ண வேண்டிய ஒரு ப்ராஜெக்ட் வந்து 2 கோடி ரூபாயில போய் முடியும், இல்லாட்டி வந்து 50,000 ரூபாயில பண்ணிருக்க வேண்டிய ஒரு ப்ராஜெக்ட் 1 லட்சம் ரூபாயில போய் முடியும். So you'll have to be very cautious about these decisions. So how do you kind of like do that? Typically, this is also a very generalized scenario. Let's say that like we come up with an architectural project and then we come up with a conceptual massing. We don't design such square massings. We come up with like much more better and efficient ways. But let's imagine for the sake of our example, it's like a cuboidal massing. So once we decide on the number of floors and then like the cutout spaces and then the staircase goes and all those things, we position it conceptually. Then we start working on the preliminary phase. That's when like let's say that we want the building to be structurally stable, right? We want it to be seismic proof and all those things. So the structural engineer might come up with like say like 4 or 5 different configurations or options, saying I've analyzed these, and then like 2 of them, the bottommost graph which indicates green, those are the efficient solutions. So you can even follow the arrow marks. So out of the 4 structural options, 2 of them seem to be working, so they get pushed on to the next state, which probably is like an architect dealing with the lighting conditions. So he comes up with like several envelope design options, and then like once like they know, okay, like this is the best on, like we'll have to increase the daylighting. So they do daylighting analysis or daylighting calculations, and then kind of like say, okay, these 2 options seem to be more efficient, option number B and option number D, which are marked in green. And then those 2 options go into the next phase where like we say, okay, I want to minimize the build cost. Minimize now, like let me meet the budget. I want to keep the budget very low as possible because the client has requested me to do so. So in that case, what I do is I do like cost estimation and all those things, and then identify which is the most cheapest option or which is the most perfect, or like there's a balance in that. Once you have identified those, then probably it gets pushed on to the energy analyst or the architect who's dealing with energy analysis and so forth and so on. He generates the MEP components in coordination with the HVAC consultant and so forth and so on. They kind of like analyze it and then find which option is like the best possible solution. And this is just a generalized scenario. Not every project has all of these, or neither like it is in the same order. It can be different. This is just an example that I'm trying to demonstrate. But the problem here is because of the sequential process, let's say that like these 2 are the options which are selected as the best one finally. But if you trace it backwards, if you trace it, you'll find that it's actually coming from a suboptimal or an option which has lower structural performance than the better one. So you're actually kind of like losing out on something, right? So how do we solve such problems for like AEC design? And essentially it need not be like a cuboidal massing. It can even be a triangular massing. It can be like a hexagonal, or like any normal building, it will be some random polygonal shape or some random configuration. So there are multiple options. It's like a humongous number of options that you can explore. So how do you do that? How do you deal with such situations? So that's when we go to other engineering fields, like say aircraft design, rocket design, automobile engineering, product design, and so forth and so on. So those fields and building fields are kind of different, but there are certain common areas which we can kind of like learn from them. So if we look at those, there is this field called generative design. So this is like an example from Autodesk that I grabbed. So this is like a structural frame of a drone. So we have all seen drones, right? Like quadcopters, even coronavirus, they're kind of like using it as a sanitizing system. Uh, so like if you want the drone to be lightweight, you'll have to modify the structural frame to be lightweight. So what they do is they kind of like generate hundreds and thousands of different options of varying thicknesses, analyze it for its weight, and then select the best solution. They've even used it in designing cycles. For example, the structural frame of cycles. If you would have noticed, all these road bikes, racers or cycle now, and they will be very easy to lift, as in you can lift it with one hand. That is because that gives it a very smooth ride, and you can go as faster as the cycle is more lighter. So they use generative design to kind of like generate lots and lots of these combinations of design options and then choose from the best. So if you look into this, so this is what they call a design space. So towards your right, what you see is you have like multiple number of design options, and then like towards your left, those filters that you see, those are the parameters which you're analyzing each of these models for. And then finally you shop for design. Okay, this is the best solution that I want. This is performing well in these aspects, so I'm going to choose this solution. Or it might even give you several number of solutions that you can choose from. And one thing to notice is that the filters here, it says strength, stiffness, mass, cost, drag, heat flux, manufacturing time, factor of safety, and all these things. So these are very, very specific to each project or each product that is designed, because here it's like the structural frame for a bike or like one particular part of a bike. This is a part of a motorbike. So there they wanted to have like a lesser manufacturing time because they want more bikes to be delivered to the market in a shorter span of time. So this is what they kind of like use in other engineering fields and product design fields. And there is also a loose term called generative design, which you guys might have come across in the internet. So data driven design, generative design, optimization, all kind of like fall under the same category. It's just different jargons used by different industry people. So learning from these, what can be done in the AEC field as an architecture, engineering, construction field in order to develop and design much more efficient buildings? So you basically have to model, and then you have to analyze the model, and then you have to select the best solutions from the model. But it's not just one model. You'll have to generate multiple models or model possibly like in Revit or Rhino or whatever 3D modeling tool you use. You'll have to generate multiple models, and then you'll have to analyze them for multiple performance factors. For example, let's take 3 performance factors: structural performance, building cost, daylighting. You will have to analyze each of these solutions for all these performance and then plot their values so that you know which one is the best performing solution on what aspect. And then based on those values, you make a selection. Either this design is the best or another design is the best. So what happens is, based on the design information that you get from these multiple analysis and selection tools. So I have this term machine learning on my topic, right? So where exactly machine learning comes into this play? So if you remember, like whenever we order stuff in Amazon these days, நீங்க ஏதாவது தேடினீங்கன்னா நீங்க எந்த சைட்டுக்கு போனாலும் there is something which is like relevant to that. If you search for a watch, யூடியூப் போனா கூட வாட்ச் ஆட் வரும், இல்ல வேற எங்கேயாவது போனா வாட்ச் ஆட் வரும், and things like that. So what they use is they grab all those data that you search for and then use that in order to kind of like train their neural network, which is like a machine learning algorithm, and then that will give you suggestions based on what you like. So same way, for every project we are analyzing so much amount of data, so much amount of like different models, and then we are making selections. So we have a pattern, right? If the value is this much, then we like this solution. If the value is that much, then we like this solution. So based on that, we can use machine learning in order to give suggestions. So the system can give us design suggestions saying that in the last stage or in the last project, this was kind of your way of designing, and then in this project you have such a design brief, so you might as well try going in this direction, or instead of a 5-floor building you can have like a 7-floor building, and so forth and so on. This is like a huge topic, like machine learning in AEC. I'm not going to dive deep into it because that might be a separate lecture altogether, so I'm just cutting short on the basics of it, and I will further go into a framework. So based on all these aspects, my current PhD work is to develop a framework or a design assistive software which will help designers take such decisions. So without much ado, I would like to show a video. So I will voice over at the back of the video so that you can um, and please let me know if you can hear the sound of the video. It just has music, but like in another video, I need voice over. So can you hear the sound of my computer?
Yep. Yep.
Okay, perfect.
Yeah, Naveen.
Okay, perfect. So what happens here is, let me put it to the correct level. Yeah. So we typically model stuff as architects. We are used to sketching, we are used to modeling, we are used to physical model and stuff like that. So model can come in multiple forms. So back in the days, we used to use sketching and then manual drafting, which is very fluid in terms of converting our ideas into like iterations. But right now, because of the technological advancement, we got much more sophisticated tools which we can also leverage. It's not that we don't have to go back to sketching. We still have to use that because like the hand-mind coordination is the best tool that you can ever have. But you also have like models to kind of like develop. So what happens is in the framework that I developed, all that you do is it was developed in Grasshopper for Rhino as well as in Dynamo for Revit. So you just feed a basic massing of the building, and then all the other systems get automatically generated. For example, the floor plates, the structural columns, the beams, and then the HVAC cores, the MEP things, and then the envelope assembly, and so forth and so on. And whatever massing shape you provide, it generates all these placeholder components for you. And one might wonder, like, this might be very rudimentary, or like, let's say that like it's very regressionistic for an architect, because we don't want someone else to kind of like automatically generate this, because we as architects are supposed to design all of these things. But this is just a placeholder so that we can get a rough estimate, because during the conceptual stages we just come up with massing models, right? It's very difficult to get cost estimations with just massing models. We get a cost estimate, but at later stages, probably say down the lane, whenever we detail out the design, our initial estimate and whatever we get at that stage might not match. So if we at least know that like these are the items which might go into the building, we might at least get a ballpark estimate. Let's say this project will cost somewhere around 50,000, 50 lakh to 60 lakh rupees or something of that sort. So we get an approximate estimate. So that is the reason for this. And once this is done, what happens is it can generate multiple models. As I told, you need not manually model everything. You can just define the rule sets and it will like generate all those models for you. And all this details about, like, let's say the wall thickness, the floor plate thickness, and all these details get stored in a cloud-based database. The reason for it, I will say, so for each of these analysis, for example, இப்போ நம்ம ஒரு பில்டிங்கை வந்து ஸ்ட்ரக்சரல் அனாலிசிஸ் பண்றதுக்கு ஒரு சாஃப்ட்வேர் யூஸ் பண்றோம், டே லைட்டிங் அனாலிசிஸ் பண்றதுக்கு வேற ஒரு சாஃப்ட்வேர் யூஸ் பண்றோம், and then for cost estimation we probably use a different technique like an Excel sheet or like a manual calculation or some other tool, some software. So all these different softwares deal with different sorts of information. For example, let's imagine that you have a Revit model. You have all the information regarding the building in the Revit model. For example, when you do a cost estimation based on the material, you need the volume of material, right? So the volume can be calculated using the thickness of the wall, the dimensions of the floor plate, and things like that. So that is there in Revit model already. So you can automate that process, get that information, and then push it to whichever tool does cost estimation. Same way, daylighting. it needs the window positions and then like the sun angle for that area, the weather data and all those things. So if you can push that into the daylighting tool, it will give results. So if it is just one option, it's easy to do. The way that we usually do, we export one format to another format, open it in a software, and then do it, right? But if it is for hundreds and thousands of options, imagine you have to open all these models separately and then export it to a different format and then like push it into different tools. For each option, each design option, you probably have to do a couple of simulations and analysis, structural, daylighting, cost, and things like that. How many times will you open, and would you even have the computational power to do that? No, right? So that's why we automate this process and then push it to a cloud server so that all the information is centralized, and from there all the analysis is done. And once you do the analysis, what happens is so this screen, it basically shows what is the length of the building, what is the breadth of the building, what is the height of the building, what is the floor height, how many number of floors do you want, and what is the area of the building, how much volume do you want, what orientation you want the building to be in, and what is the energy consumption that you want it to be, cooling load and daylighting factor, and so forth and so on. So you basically can adjust all these things in real time. So what will happen is after you adjust this, the system will generate a lot of different design options based on how much ever you filter out these values. So in a couple of seconds, you'll be able to see those options. So these are the design options which are generated from the system, and then it's comparing all of these design options. So on the left side of the screen, you see like a couple of different options, right? Like 12 different options. It's more than 12, but just for the sake of fitting it on the screen, I've shown 12 as a sample set. All those, each of those design options are marked as points in this. You can call this a three-dimensional graph or a scatter plot. So here it's comparing for energy consumption, cooling load, daylighting factor. So it's saying that like if you choose one design, it is performing this much in this aspect, this much in this aspect, and this much in this aspect. So basically you can simultaneously compare multiple options and then choose the best solution that you want. And this might be a little less intuitive for us to understand, right? As in like we don't know what these dots represent. So I developed a front end which will allow you to kind of like interactively change all these values. For example, you can say, I want the energy consumption of the building to be within this range. I want the heating load of the building to be within this range. I want the annual daylighting factor to be within this range. I want the build cost to be within this range. And then it'll identify the perfect solution which matches all these criteria. And when I say perfect solution, I don't mean to say that like the computer will automatically do all this for you. You are the one who are modeling it. The initial massing is being modeled by you. And another important factor is that like this is not a single step process. So once all these are generated, it's not just like you are pushing everything as it is, which is generated by the computer. There is also human interaction. So you can go and customize whatever you want inside of each options. You can even customize it for multiple options at one go. So that you say like, I don't want this many number of columns, or I want like the bedroom to be this size or the bathroom to be this size. You basically can model on top of the generated solutions. And finally, what you get is these results here on the interactive front end. And it will also give you details of how many number of floors are there in the building, what is the wall window ratio, what is the wall type, what are the materials which go into it, what is the window type, and each of these design options are like represented by these dots here. And once this is done, the machine learning part that I was talking about, like same as how Amazon shopping kind of like uses. So same way you can query the data. You can ask the system saying which design option has the most energy efficiency, or which design option has the lowest daylighting factor, and it'll identify whichever design option has that. And we'll even say which design option has the highest build cost. You can kind of like not go that route, and then instead explore the other design options and so forth and so on. And since this is hosted in a cloud-based server, one other important factor is that it can be accessed via multiple devices. Like you can access it via computer, you can access it via a web browser, you can access it via a tab or even a phone, and then you can make changes interactively on the go. So if a structural engineer wants to say that I want a building which has a maximum structural performance, he can kind of like change it on the go and then convey his information to the architects or to the electrical engineers and so forth and so on. Because like the reason that you'll have to convey these informations is that for example, the structural engineer might say for the building to be structurally sound, I want the wall thickness to be this much. Let's say like I want it to be 9 inches. But the energy engineer might come and say, or the architect who's working on the energy analysis might come and say, no, I can't have such thick walls because like that will increase the amount of heat retention. I want lighter walls. So there is like a conflict, right? So you need to find the perfect balance. Either it is 9 inches or somewhere in between 12 inches and 9 inches. Wherever it is in between the 12 and 9, that is very crucial to find in order to avoid such conflicts. So this is one part of like just a very brief intro of data-driven design. And going back to the presentation, now I'm going to kind of like increase the scope of the presentation to robotic construction as well. So right now we understood, as in I hope that I was kind of clear. I am not sure if I rushed through it a little bit, but the idea was that data-driven design is needed in the future for the building industry because most of these objectives in the design brief are going to be very, very quantitative, and there are also going to be qualitative aspects. But if you want to sort out the quantitative aspects of design, you need data-driven design because you need to generate hundreds of combinations and then make some selections. Imagine it analogous to shopping. Let's say that you want a very good dress for a meeting. எனக்கு வந்து ஒரு நல்ல ஷர்ட் வேணும், நல்ல பேண்ட் வேணும், but I have a budget and I want this color or this material. So there are lots and lots of variations, right? You can go to like Pondi Bazaar, or you can go to like some high-end shop, or like you can go to like any shop. If you go to 10 different shops and then like look into all the options and then make a decision, that's always going to be better than just going into one shop and making a decision, right? So that's the fundamental idea behind why data-driven design is needed in AEC industry. And specifically, if we go to robotic construction. So here I will talk more about the NASA project, which I was part of, like a very teeny tiny role. So where we were tasked to design a building to be 3D printed in Mars. So here in the US, NASA has a goal of sending an autonomous rover somewhere down the lane in like 6 to 7 years or 10 years might be. And then they want to construct research facilities in Mars. And one key thing is you can't kind of like carry construction materials in the rocket, because every single kg in a rocket counts for cost as well as it impacts the rocket's design. So it can carry only very light loads. So you can't carry bricks, you can't carry concrete, you can't carry sand and then go there and construct. And neither those materials which work on Earth work on Mars, because the environment in Mars is totally different and every single detail is totally different. So you'll have to find out something which is in-house. So we devised a method where we can dig things from Mars and then kind of like make concrete from Martian soil and so forth and so on. So I wasn't part of the material study, but I will explain what happened. So the reason for robotic construction, the reason that I told this was things might kind of like sound very fancy or atrocious, because like we have a lot of valuable human labor, so why to use a robot all of a sudden for construction? But certain situations demand robotic construction, for example remote situations. And then like for example COVID-19, every construction site is kind of like closed and there is no human labor allowed inside. And if you stall a construction project for beyond a certain number of days, you incur humongous amount of value loss. So if you want to continue construction, there are certain ways you can remotely do this. So robotic construction is one option, which might be, it's still in the stages of infancy, but it will get there someday, and it will be used for very specific use cases. I wouldn't say that like this is going to completely replace human labor. It is just for very specific use cases. So for robotic construction, one key thing is instructing the robot. Same way, for example, imagine we driving a car. We have control of the steering. We can either turn left, we can either turn right. For two-wheeler road now, we can either turn left, go straight, go forward, stop, or something. But here we'll have to instruct the robot what to do at what time, and that has to be in a language that the robot understands. So as you know, building kind of like has multiple components, and we'll have to design those components in a way that can be either 3D printed or prefabricated or assembled using a robot. So as you can see, these blue lines which indicate that we call it as toolpath. So I might use this term toolpath very often in the forthcoming slides. So that's why I'm giving a very brief overview. So toolpath is like, imagine it to be like a Google map. So whenever we are navigating somewhere, we turn on the Google map, it shows a route, right? Same way, a toolpath is like a Google map for the robot to transit on a certain direction and then do some certain tasks. So back again, AEC industry. So in the previous example where we were designing typical buildings like office buildings, residential buildings, we were just dealing with the first two parts like architecture and engineering until the detailed design stage. But for robotic construction, it is very, very important to kind of like think about like the construction aspect. Even in traditional construction, it is important, but for robotic construction, it is extra important because of certain reasons. For example, I will explain what the reasons are. In a traditional construction process, we have a design brief, and then we model or 3D model or generate some couple of different design options. We do all sorts of analysis and then analyze those design options. And then once we optimize the solution, as in optimization is a term where like, okay, there are these trade-offs or like giveaways between two things. If you want to increase one thing goes down. If you want to decrease one thing goes up. So how do you attain a balance? That is like a rough way of explaining optimization. So optimization kind of like finds the perfect balance between the two quantities. And we simulate the construction activity, which is basically can it be constructed and what are the logistics involved in construction, how many trade contractors we need, how the site has to be prepared, and a lot of other things, and then we construct. But in robotic construction, what happens is there's a design brief, same as we do in traditional construction. We model and then like generate a lot of three-dimensional models, and then we do performance analysis. But here is a slight change. You'll have to simulate it or analyze it for structural, environmental, as well as constructability, because it is like a robot which is going to do all the activities. You need to be sure that it will perform all the activities in an intended way and not do something haywire. So you have to simulate and you have to analyze the constructability as well, and then optimize and then construct. So this might seem like a very minute change, but it has a lot of impact. How is this is just a video showing 3D printing of concrete, a very simple cylinder. So let me play that. So everything might seem like it's going good, but at one point in time it might fail. So the material seemed like it worked, but at one point in time it failed. So this is the reason that we'll have to figure out, we'll have to be very sure if the robot is going to do what it is intended, as well as the material will behave the way it is to be modeled or the way that we envision the material to behave. So in order to avoid such mishaps, this is just a simple cylinder, right? Imagine constructing an entire wall and then it falling or tripping off completely. It's waste of material, and if someone is standing next to it, தலையில விழுந்துச்சுனா அவங்களுக்கு அடிபடும். இந்த மாதிரி நிறைய விஷயங்கள் இருக்கு இல்லையா? So we'll have to think about all these things. So there are multiple systems involved in robotic construction. For example, we have to design the material, we'll have to design the printing features, and all these variables here, you need not worry what exactly it means because I will explain them in future. So material properties, toolpath design, and things like that, bead shape, and all those things I will explain in the forthcoming slide. So all of these factors impact one thing called the building design, which is the shape and the size of the building. Because same as us human beings, we have a reach, right? என் கையை வச்சு நான் கொஞ்சம் தூரம் தான் வந்து ரீச் பண்ண முடியும். I have like a limit, freedom of movement limit. So same way, a robot can only extend until a certain distance. If it is on wheels, it can move away, but like if it is on wheels, it will start vibrating. and if it vibrates, then like olunga print pannadu, olunga assemble pannadu, there might be a lot of mishaps. So it has to be static for certain use cases, and if it is static, it can reach only until a certain degree of freedom. But your building can't be like a tabletop model, right, for the robot to kind of like just build it in a very small scale. So you'll have to design a building where you can move the robot time to time. At the same time, it can reach to certain places so that it can print all those shapes. So you need to kind of like think about all those things. So things like designing the material, you need to know what type of admixture. So typically concrete curing, we mix concrete and then like admixtures and binding materials, we pour it. Reinforcement block vectors, we pour it. But in terms of additive construction, let's say robotic concrete 3D printing, there is no reinforcement at all. So you're basically 3D printing. The idea of 3D printing is that it deposits material layer by layer. So here we'll have to design the material in such a way that concrete, as we all know, gets cured in a particular time. So we don't want a concrete mix which cures while it is coming out from the tube, because that is going to clog the robot. Neither we want a concrete which is setting so fast, because like once the moment it comes out, or setting so slow, because it has to be in the right consistency to support the previous or the other layer. For example, let's imagine that like we printed one layer. If it is like very slimy, tanni mari irunchuna, you can't print another layer on top of it. So it needs to cure within a particular time. So that is what we design in terms of like where is the robot, what type of mixers we use. If there are two different types of materials coming in, we have to use multiple equipments in order to mix it at a particular ratio. நம்ம அம்மா வந்து அரிசி மாவு அரைக்கிற மாதிரியே இமேஜின் பண்ணிக்கிறோம். கிரைண்டர்ல உளுந்து ஒரு குவான்டிட்டியில போடணும், அரிசி ஒரு குவான்டிட்டியில போடணும், தண்ணி ஒரு குவான்டிட்டியில ஊற்றணும். அது மாதிரி வந்து அந்த செட்டிங் டைம் கரெக்டா வர்றதுக்கு யூ ஹேவ் டு மிக்ஸ் ஆல் தீஸ் திங்ஸ் இன் அ பர்டிகுலர் வே. So all those things have to be thought about, and how it is going to be connected to the robot, and like how the robot is going to receive these instructions and so forth and so on. So if you remember 2 slides ago, there was a term called bead length, bead diameter, and all those things. So bead is nothing but each of those layers. So this is in section. ஒரு layer print ஆகும்போதும் has to be in a particular form. So if you can see, the bottommost layer is like very small because it's taking so much load from the top, and as it goes up, it's kind of like getting larger. So when another layer is printed on top of the topmost layer, it will also shrink a little bit. So we need to design the material so that it doesn't shrink so much, because we need the a number of layers should reach a particular number of or particular height of the wall or something like that. So all these things, how time impacts all these things. For example, let's imagine a square as seen in one of those pictures. So if the robot is taking like say 2 minutes to transfer from point A to another corner of the square, on the 2 minutes the first layer has to get cured, and then so that the next layer, when it starts printing on top of the pre-existing layer, it will kind of like be able to withstand. So the time management, that is very crucial, and we can't kind of like gauge it intuitively. We'll have to resort to simulations and physical tests. So what we usually do is, so we print out samples like these, a lot of different samples, and then we test it out for different conditions. We do compression test, we do kind of like breakage test, we do shrinkage test, and then concrete slump test, and all these things. And we also have to deal with the logistics. So once you have all these things figured out, if it is going to be on a mobile site or on a different site, how would you transport all these equipments to that site? How are you going to arrange all these things and things like that? So it can be as trivial as imagining a car park car apartment car parking. If there are 2 cars on the sides, you'll have to find some way to maneuver, right? Same way, you'll have to decide on each and every detail of what is the distance between the 2 robots, what is the distance between the robot and then the truck, so that it doesn't have any impact on the truck when it moves around. It doesn't kind of like hit any adjoining object and things like that. So you'll have to figure out all these details. So in order to do this, in addition, we also had extra conditions, like we were designing for an extraterrestrial planet like Mars, which brought in totally different designing systems, totally different material systems which had to be designed per se for Mars, and different printing systems. So with all these things, how typically additive manufacturing works, like construction la vandu concrete 3D printing paathom, but like when we talk about 3D printing, one thing that comes commonly to our head is like, let's say plastic 3D printing or metal 3D printing. How does those industries work? So we have this basic protocol. So we generate a 3D model, some random shape that you want to 3D print, and then we slice it, basically cut it into sections, like in sectional view. And then you will have to translate those sections into root codes, or like the basic thing as a Google map, so that the robot can kind of like move along this axis. So it can be something like you're instructing the robot to say, go straight, turn left, slow down, take a right, and things like that. You're basically instructing the robot to follow a map. And once that is done, then like if the robot is able to do every single layer according to these instructions, then you get the object. This works perfectly fine for a plastic, because there is humongous amount of data about the melting point, boiling point, or not boiling point exactly, melting point, or like the setting time of metals and plastics and so forth and so on. And they're very, very monolithic materials. But in the case of buildings, we are dealing with multiple materials, right? We don't deal with something like plastic which sets instantly. So that is a different problem. And then like depends on the shape. For example, let's consider a very teeny tiny example. I know that like architect Kavita was also one of the panel members before she, so you guys might have already heard a lot about 3D printing. So this might be something which is an addendum. So you have like, let's say like a very small tabletop model or a miniature model of a statue. So how you slice it is you basically slice it at different angles. But one problem is if you see near the shoe of that person, everything is like joined. But if you look at the in between those legs, wherever there's gap, there is like no material here. If you can see my cursor wherever I'm hovering, there's no material which is to be deposited here in between this knee portion. So same way, what happens is apart from the directions that you give to the robot, which is called a G code, you also need to give the robot an M code, which is basically stop the motor, stop deposition, or turn off your motor while going here and things like that. For example, if you don't want to deposit materials in between these two legs, then there has to be a clog, or the outlet has to be closed at that particular instance. So you don't manually go and close it. Instead, you program the robot so that it automatically closes at that point in time. So that is called an M code. So a G code and an M code together, every robot has something called an inverse kinematic system. Not going too technical into it, it's nothing but, as you can see on the right side GIF, if there is one point, say the red point, as I told before, I can reach my arm only until a certain distance. So on the red point, the deposition point, the robot can reach only until a certain distance. So if it is beyond that distance, then the robot can reach. So it has to kind of like solve for all those things, and then like your 3D model has to fall within those limits. So that is the solver which every robot has, and then that kind of like takes care of the motion solving properties of how to kind of like address those problems. And then for each of these, they have different tools. For example, they model using SolidWorks, Inventor, Rhino, SketchUp, Revit, and whatnot. And then they kind of like use tools like Cura, MATLAB, or like custom written codes in Python or Grasshopper or Dynamo for slicing it, basically cutting it into this axis. And then they use several other tools like Cura or Grasshopper for kind of like converting it into a machine code. So once that is done, what they do is they kind of like use a robotic motion solver in order to kind of like change or kind of like print all these things. So each of these has these different data translations from one format to another format and things like that. And if it is like the scale is increased, for example, it's not just 3D printing, it can even be like milling or routing and things like that. So if you look at a typical car assembly lane, you have things like digital twins. So they basically simulate each and every movement of the robot before it is being performed. So they create accurate to the inch precise models of the entire workflow along with the robotic movement. So if you translate these processes into additive construction, it doesn't work exactly the same per se, because we same as them have a model, and then we can slice it, and then we can kind of like print it, and then we can construct it. But the problem is we're using concrete or some other material like clay. It doesn't kind of like support all these angles here. So what happens is it might fail because like concrete, it tends to address, as in kind of like get impacted by gravity. So if it doesn't set within a particular time, such edges might fail. Or per se, if you say that like your model is hollow, then your entire inner structure will fail because there is no support on the inside, neither the concrete is set on time. So how will you kind of like deal with these? So let's say that like you have like a particular slab, and then you kind of like slice it in a particular way. So you slice the model in like different ways. There are like different ways that you can slice it. Like you can either slice it like A, or you can either slice it like B. This is in plan view. So each layer has to be filled, right? And then once that is done, then you translate it into a machine code and then construct it. So option A is very solid. Option B is like much more lightweight. So if you look at these comparisons, what happens is for option B, the structural performance might be very high, but it has complex robotic maneuvers because it has to do all these zigzag lines. Imagine you going in a car at a particular speed, and then like you suddenly make a left turn, you jolt, right? There is a vibration. So same way there will be like vibrations whenever the robot turns. So because of that, there will be concrete deformation, and that might be a problem. So same as we dealt with trade-offs in like the traditional design, here as well we have like trade-offs in robotic construction, because like this option seems to be good at structural performance, but it was also creating other problems like robotic vibrations and concrete deformations and so forth and so on. So how do you address these? So these are images from our NASA competition where we printed like huge scale samples. So as you can see in one of those corners, you can see this concrete is kind of like over extruded on the left side corner here. That is because of the acute angle that the robot had to traverse. So, and then another problem was that because of the angle of the extrusion, there were failing of concrete at certain places. So if you translate this into design variables, fillet radius at the edge and corners is one design variable which is impacting, and then the robot speed at the corners is also another design variable which is impacting. So you'll have to control these variables, right? And then like the material consistency. So all these things, as I told, there are different things to be designed for robotic 3D printing or construction. So as you can see, these beads fail because like it's a tapering angle, and then they don't have any supporting structure beneath them. So there's a lot of like such simple or like even like minute complications which need to be addressed. And the sectional detail, it can't have it here. If you can see my cursor, it needs to have a pointed edge here. It can't have a flat roof because it doesn't have any support system underneath. And one other thing was we were using unreinforced concrete structure, so we have to design the structure in a way that it doesn't require any reinforcement per se. And typically, concrete construction, 3D printing, it has been there for almost several years, like 5 or 6 years. From the past 5 or 6 years, it's been really famous. But one problem is that most of those concrete 3D printed structures are divided into modules, and then each of those modules is divided into separate parts, and then these parts are printed in a different orientation so that they don't have to deal with like the gravity effect or the tapering angle and things like that. Once they print it, and then once it is left to cure for like say several days, 3 or 4 days or 5 days or 28 days, then they kind of like tilt it or change it its orientation and then assemble it back together. So this is how concrete 3D printing has been developing over the past but our ambition was that like we never do any tilting or orientation. Instead, we start printing whatsoever and then not use any reinforcement or unreinforced concrete structure to be the correct technical term. And we wanted to kind of like do that. So in order to do that, what we had to do was we had to create a digital twin for the toolpath simulation of how the robot will behave or the material will behave when it starts printing. So we had to kind of like create a three-dimensional simulation of the entire process, same as how they do in the car industry or in the automobile or aircraft manufacturing industry. So in order to do that, so this is like the output which came out of the competition. So the competition had two levels. One was a virtual construction level, and then the other one was an actual construction level. So virtual construction level, we had to submit all those like soft copies of simulations and analysis and so forth and so on. actual construction level, we actually had to print out whatever we proposed. So this was the design solution that we proposed for the actual construction. So if you can see all those like grooves that you see there, that is for cold joint, because the competition happened over a period of 3 days. NASA intentionally kind of like asked us to stop on every day evening and then start printing the next day. So if you leave concrete 3D print for overnight, then it gets cured. And then if you start printing on top of it, there might not be structural addition between two layers because one is already cured and one is like perfectly new. So we have to design these grooves so that they have some sort of interlocking mechanism which account for the lateral loads so that they don't tilt on the sides and things like that. And we also had to create a digital twin of the overall setup where like the mixer, we had two robots, one for 3D printing and one for kind of like placing the windows and stuff. And same as before, we generated a lot of different design options and then we analyzed them for structural performance, environmental performance, and constructability, which is basically robotic toolpath and logistics and setup. And we kind of like generated multiple design options and then did the same analysis. And finally, we found out the best solution and then simulated the construction. So the generation part included like all these interiors, like the floor plate, the wall system, the furnitures, and then the staircase system, the floor plates again, and then like all these other interior systems. And then these things, that triangular things that you see, those are like the what is it? The emergency shutdown systems between each of these modules. So we designed the building to be modular. So each of these circular blocks, because of like several safety precautions, if something bad happens in one module, you can always shut off these doors so that it doesn't, if there's a fire, it doesn't spread along to the other modules and so forth and so on. So we have to think about like the emergency modules. And then like the HVAC systems and MEP systems, and then like hydroponic garden and like a structure. So this is like a small
Builds
video
on our current research to develop low-cost housing on Earth using parametric BIM design.
Kind of like shows how all these different design options were developed, as in multiple design combinations were generated. And then we also kind of like mapped all the variables, like what is the radius, what is the distance of it, and distance between the modules, and if it is a straight wall or like the taper, and like what is the tapering angle and so forth and so on. So 60 intersect is like an option where two modules intersect together and have a tapering angle of 60 degrees. So we had to kind of like do all these simulations and then find out what exactly is their structural limit and like how they perform under adverse conditions and so forth and so on. So once this was done, our structural analysis, we used Nastran, and MATLAB is like a code writing tool which we used. And structural analysis part was done by one architectural engineering colleague of mine. So I was just responsible for coordinating this entire BIM process and then gathering all this data and then creating in a system so that everything can be automated. But each of these had subject matter experts, which means they were people who were experts in those fields who dealt with each of those aspects. And for constructability, we used Cura and HAL, where like each layer is simulated and we kind of like know what kind of like is done. And this is just a diagram showing like all these tools were connected to a centralized cloud server so that they exchange data between each other. And same as before, like we had a system which will kind of like give us different parameters. So we can say we want a design option which will kind of like have the lowest machining time, or 1 second, sorry. Yeah, so same as before, in the previous example that you saw, it had like energy, cooling load, daylighting, and build cost. But here you have other different goals like machining time, material cost, and compressive strength. So you can say I want a higher compressive strength, lower machining time. You want the robot to print it within a short span of time, and then you want the material cost to be lower. So based on this, the system will kind of like identify which is the best possible solution. So once this was done, then like we finally 3D printed our entire structure at the competition, which is, so we had, as I told, we had two levels: virtual construction level, which was like simulated conditions from Mars, and an actual construction level where we construct an actual prototype, a full scale 1:1 prototype at one of the NASA facilities. So this was the option that we submitted for actual construction level, and we had to simulate it for like all these toolpath simulations using different tools. And this is how like all the simulations were done within Revit. So we used Revit as like one for all BIM platform where everything was performed: analysis, toolpath analysis, cost estimation, and everything. So we developed a code there. And once that was done, what we did was we also did 4D simulations. So this is like a 4D simulation which says like the truck arrives first, and then the silo is unloaded, and then like there's a mixer arriving. So it's basically a schedule of events or a sequence of events which are to be done, and all these had to be connected. And we did a simulation or a 4D simulation of the entire process where every single thing was simulated, including the robotic printing. So right to the safety systems, we had to kind of like simulate the barricades and everything. So one robot was used for 3D printing, whereas the other was used for placing the windows. So once the simulation was done, then we kind of like had to send all these details to NASA so that they could ensure that everything is on track before we actually print it. So we used a BIM framework right from the generation until the construction stage, so that we integrated all these tools together so that it fully supports a data-driven decision system or a data-driven design system. And this was a simulation, and this was our actual setup. You can see there is a very close resemblance with very minor deviations from the actual plan. And these are images from like the competition where we printed our entire structure within like 16 hours cumulatively over the span of 3 days. And that way we kind of like produced the world's first fully enclosed tapered concrete structure, which was 3D printed without any support structure. So one might wonder that like there have been already a lot of like bridges and things 3D printed, so we can't claim that this is like the first concrete 3D print, but it is the first which was 3D printed without any support structure, and that too have a domed or like a tapering roof. So that was one thing that like kind of like motivated our group very much. And we reached the finals, and then we finally got like the second place. Like another firm which kind of like competed with us got the first place, but it was kind of like well received, and it was indeed like a platform that could be experienced. And they also did some structural test where like they put a huge caterpillar machine on top of it and then tried to crush it. And for an unreinforced concrete structure, it lifted the trails of that machine for 48 seconds, after which it crumbled. So they basically identify the weakest point so that they can identify like a threshold. And just to give you a sense of this, this 390 here indicates 3 means excavator and 90 means 90 tons. So it's 90 metric tons which is put on top of the entire structure. And with that, I conclude my presentation, but I also have one video which might be playing at the background while you can kind of like, I'll take questions from you guys while it's playing. So this is a short video which kind of like was made by the university for depicting
2019 in Peoria, Illinois, a team of Penn Staters made history. They became the first ever to build a fully enclosed 3D printed habitat at architectural scale without any support structure beneath. It was the final round of NASA's 3D Printed Habitat Challenge competition to design and build a structure suitable for Mars. The achievement, a culmination of years of research and design from an interdisciplinary team led by Penn State faculty.
The idea here was not to just design a common building, but to innovate the construction process and the architecture. So I got interested in digital fabrication, and particularly on the 3D printing of concrete. We made what we call functionally graded materials. The idea is that you replace part of the aggregates in the concrete with a lightweight material that has good insulation properties, for instance, cork.
I had a vision to transition seamlessly between concrete and glass without the use of any mechanical frame or bonding agents. That would make such a difference in architecture if you were able to do something like that.
We developed what we call Marscrete, which is a kind of concrete that's made of materials that can be found on Mars. Constructing a habitat on Mars had new challenges for us. When you go to Mars, you're dealing with a lot of loads that we designed the structure, we designed the material, we designed the reinforcement to resist those loads so that we provide a safe structure. My role as part of this team was to really think about the systems aspects. How do we go from the micro scale to the macro scale? That's a big systems challenge.
Another revolutionary approach was to design the building and the process simultaneously using artificial intelligence and building information modeling. This enabled the team to produce a building that not only pushed the limits, but in fact could be built. There were 8 levels in the competition that involved nearly 80 teams from around the world. Only 2 reached the final round.
We only got our robotic arm about 2 weeks before we went to the competition, so we were learning things in real time.
Both teams set out to build their subscale structure in just 3 days.
We have never actually tested printing the entire thing.
By day 3,
It was the most difficult one. Because going very slowly, it seems that it lasts forever.
the team finished with just 11 minutes remaining on the clock.
Seeing everything all together at the same time was like seeing a dream coming true.
We're very proud we've achieved this goal of creating the very first building that is completely 3D printed, including the roof.
This is something that hasn't really been achieved on this scale before. Look at the challenge that was set before us, the team that we brought together, and then the competition venue. It was really quite amazing. I'm really proud of my team and how we were able to achieve this. Everybody was needed. Every person on there was vital. If we would have missed one of those skill sets, we couldn't have done it. Being a part of that and being a part of the success of that was very rewarding. Once in a lifetime experience, really.
We can really push the limits. What we think is the limit today, the innovation of tomorrow, and then just the everyday use material the day after.
I think that someday we would be able to build on Mars and eventually live on Mars. And looking forward to that day.
Nothing is impossible. We can do everything in a team as long as we are dedicated and responsible for what we have.
We've used the competition to accelerate our research. This has enabled us to do our research much more quickly and gain more visibility.
Our mission is to use all these innovations and the experience that we have gained to make an impact, to make a difference in the real construction.
And it allows us to unite forces between various disciplines and bring ideas together.
So that's all that I had, and hope I didn't kind of like bore you guys on a Monday morning. And I'm open to taking questions. Hello.
It's Monday morning for us, but it's quite late night for you. So I hope you are still awake and energetic after this amazing presentation of yours. I think it's one of the most well documented, well organized, and well narrated presentation in our sessions, at least until now. We had quite a few interesting people come in and see you present the way you presented today. It is quite remarkable the way you have tried to put everything together. Quite an extremely intense topic as well. Like, it's not for the extremely, I would say, light-hearted people, but it's quite an intense topic. And the way you have put this together within an hour and given us this idea of how architecture is going to evolve eventually with the technological advancements, and we have to slowly start moving towards an extremely different platform as well. We cannot still sustain ourselves in the regular way of conventional thinking that we are still fixated upon. So I guess it's quite an interesting presentation. We are getting comments that you'll be a great teacher as well. If you ever want to come back, if you ever feel like, I'm sure you will be a great teacher, is what we're getting comments on our messages as well, the way you're presented. First and foremost, I would like to congratulate you as well in terms of your growth pattern for the last 5 years, how you have evolved after architectural education in Meenakshi. We're quite happy with the kind of growth that you've gone through in terms of fulfilling your ambitions and working towards them. Like, it's quite ambitious and quite good to see that you're working extremely hard towards it. Especially your final project that you come across, the NASA competition, gives us a real picture of things to come. Like, it's not a dream far away. It's quite real and quite it's surreal as well to see that things are happening at such large scales as well. We have a few questions as well from our students and from a few of the other participants as well. First and foremost, I think I'll take one from our own professor, Vidya ma'am, who wants to congratulate you for your growth, as well as we already mentioned, and the way you've connected with the students and the clarity of conveying information. And she also says that you'll be a great teacher as well. So she wants to know regarding the softwares that you have used for thermal performance analysis of the buildings, like specific softwares, or is it just everything is Rhino based?
So like it's both Rhino as well as Revit based. So we use Energy Plus for energy modeling, and then there are very specific instances within Energy Plus which are used for thermal analysis. And we also use in-house codes for thermal analysis. For example, that's what when I said during my master's, I was focusing on building physics, right? So what I did was, like, there are these sophisticated proprietary tools which have some sort of equation which is being solved at the back end. So we try to understand the equation and then simplify it so that we can use it during the conceptual phase. For example, you don't see many people using Energy Plus or any other complicated tool during the conceptual stage. So we create our own in-house codes which are simple to run and very fast, and that's what we used during the early stages. And then during the later stages, we used Energy Plus, we used DaySim for daylighting, and then we also used another it is not actually a tool, it's more of like a daylighting calculation method called Radiance. So we used that for daylighting calculation. And for structural, as I told, we used Nastran and MATLAB, which was dealt by the structural engineering team. And I would be making no justice if I don't show this, but I really want to kind of like share one more thing. Just like a quick slide. So the NASA competition, as I told, I played a very, very tiny role in the competition, and it was like a humongous team which was kind of like leading the effort, almost 25 to 30 people. And I just wanted to showcase these names so that, like, because most of them are students who would be going to their next phase in the career, so they can always try to kind of like keep in touch with these professors or look online about their work so that they can kind of like when they apply for their masters or like future career prospects, they can look at these people. So this is the entire team which worked on the Mars habitat team. This includes professors, PhD students, postdoctoral students, and then graduate students who are master students, and then like people who are like lab assistants. So this entire team kind of like played a huge role. And this is like a multidisciplinary team. So we had structural engineers, we had architects, we had electrical engineers, we had even a agricultural engineering professor called Randall Bock, who was helping us with the logistics part because they deal with heavy agricultural machinery. So he was helping us with how to kind of like deal with the logistics of the robots and stuff like that. Sorry, I digressed a little bit away from the question, but
no, I guess I think it's good to see that it's a large team because things like this, it's not a single man, it's not a single man army, it's not like the ones that happen in movies, but it's part of a large team. So it's good that you showed us the effort that goes in constructing even a singular building like a structure on Mars. It takes quite a bit of effort and expertise from multiple people as well. So moving on, we have similar questions in terms of what kind of softwares have you used in terms of for best simulation. We have one from Priyadarshini, a student as well. Like what are she's saying that she's already seen your work, experienced your work with what would you suggest in terms of which software is the most efficient and user friendly with respect to simulation and energy modeling?
So for simulation and energy modeling, like the go-to benchmark standard is Energy Plus. That has been a tool which has been developed with efforts spanning across the last 40 years. So they have continuously iterated over the tool. So that's the most robust tool in terms of energy modeling. If you want to sustain in the industry in terms of energy modeling, if you know Energy Plus, like the in and out of Energy Plus, then you would be considered like a very well-received candidate. But there are other options as well. There is one tool called IESVE. It's called Integrated Environmental Simulation Virtual Environment. That is IESVE. So that's also a proprietary tool which is based off Energy Plus. So Energy Plus is like open source. It was led by the US government in association with like European agencies, as well as from India. There has been a lot of contributors to Energy Plus. So Energy Plus was used as a baseline standard, and all these other proprietary tools are based on the same standards. So they just change the UI and certain equations, and then they create their own tool. So IESVE and Energy Plus are two tools which are used for detailed energy simulation. If you want early stage energy simulation, there are Rhino-based plugins like Honeybee, Ladybug, and all these tools. But off late, learning Dynamo and Revit might kind of help you understand the entire process, because more than just learning the software, it's more of understanding the process. There is a very common mismatch of considering Revit as an equivalent of BIM. BIM is more of a theory, whereas Revit is just a tool. So CATIA is another tool which you can use. So it's more of understanding which tool to use at what place. So for energy, IESVE, Energy Plus. Daylighting, Radiance, Diva for Rhino, Honeybee, Ladybug. And for cost estimation, you can either use Excel, or there are other scheduling tools which have cost estimation inbuilt within them, like Primavera, Startpro, and all those things. And for 4D simulation, for typical 4D simulation, people use Navisworks. But for this process, we kind of like built our in-house framework within Revit, so that we can do everything within Revit instead of having to go to Navisworks and then try to do all the simulations there. So we try to kind of like keep it a one platform, do all kind of thing.
Yep. I guess people who are interested in it, like someone who's really specifically want to get into simulations, should approach you as well to get some insights in terms of how to start off with the basics, because quite a few of our students are coming up with those questions related to how do you start off on exploring BIM and even digital fabrication, or how to start off learning how to model and stuff like that, because that's the basics of it. People need to understand that. So I'm sure that if anyone who's interested should approach Naveen, I'm sure he will be more than willing to help you guys in terms of starting off at the basic levels. There are few more questions related to 3D printing as such. There's one from one which goes on the lines of, is there going to be any general hazards or any drawbacks if we move from a conventional method to a robotic system in the future? Do you feel any drawbacks that may come across as well? just forget about the fact of losing on labor. We're not considering that, but anything else related to that.
So the thing is, there will be, instead of drawbacks, we can call it challenges. So even the very trivial tasks that we do using manual labor will become very complicated using the robots. So we'll have to kind of like take much more leaps and bounds in terms of like the technology to do that. For example, with concrete, the robot functioned in this way, but if it's a different material, it's totally different. And then concrete 3D printing is just one subset of robotic construction, right? There are other ways of fabrication, aluminum bending, and then there are factories which assemble like prefabricated modular walls together. They lift it and then they assemble it together and things like that. So for each of those different types of fabrication methods, there'll be different challenges. And I think it will help the construction industry, and it's going to kind of like require a lot of, as you had correctly pointed out, those who adapt to the change and those who kind of like learn these skill sets will be able to kind of like take the lead. And conventional construction will be, it's there to stay for at least the next 30-40 years. We won't see any like massive 3D printing, or like there are few things happening in Dubai, but those are very specific projects. It might be for very specific use cases, like say rehabilitation projects, like tsunami rehabilitation projects. They had the same house which was to be replicated in hundreds and thousands of different typologies. So in that case, it's easier to program the robots to repeat the action. So if it is repetitive, it's going to be easy. But if it is going to be like customized and everything, then it's going to take a little bit of time to adapt to that. And in terms of like thinking, as I told, from traditional point of view and robotic construction and like the way that the project is going to be built has to be thought early during the design stage. Typically right now we think about construction and construction management only when we have a detailed design, right? But like when we switch on to robotic construction, we'll have to start thinking about it right when we decide the basic massing of the building, because that is going to be dictated by the robot and other features. So that's going to require a little bit of paradigm shift in the way we think about design.
I think we're not too far away if you look at the way people are exploring the options of driverless cars as well. For a matter of fact, it's completely AI driven. It's the near future. There are quite a bit of cities in Europe, especially Helsinki, for a matter of fact, which is moving towards this AI-based driverless car systems. They're designing cities. The city planners come in and take up the role of designing cities in such a way that you let AI take over as well after a point of time. It's not, you have to consider them as an important parameter as well when you design a city or design a new township, for a matter of fact. We cannot still stick back to 1960s modernism style of Le Corbusier designing sectors and stuff like that. There are multiple parameters that have come up that we'll have to consider as well in terms of designing our cities as well. Especially, as you mentioned earlier in your presentation as well, that at least for a matter of fact, in 2020, 2025, possibly robotic construction is much more a specialized event kind of tool that you'll use. Places where you cannot access, like maybe as you said, extraterrestrial neighborhoods, or maybe during hazards and stuff like that. So possibly it's a great benefit for us as well, where we can use these systems where we cannot reach directly. There are quite a bit of scenarios that can come across, especially during the pandemics or even disasters as such. But it's great to know that people are working on those lines, and I'm sure, as you mentioned as well, that in the next 30 years, maybe 2050, maybe in our generation, we'll be able to see that it's become part and parcel of our construction industry as well. I'm sure, I know for a matter of fact that in Europe or UK, at least they have moved towards an entire BIM-based office setup in 2016. So they have already made that change, and I'm sure we'll move towards that as well. We have a few more questions related to how AEC is going to transform over the years, how AI-based design is going to overtake human-based design from concept to execution. I think you have covered most of those questions in your presentation as well. Also, there's a similar question in terms of materials. How do you look beyond concrete? Is that the only material? I think you mentioned that in your previous answer as well, that concrete is only one material that you have explored, but there are multiple other materials and which have more or less different principles, different characteristics as well. So I think those questions are already answered. There's one interesting question in terms of, I think it must be a student, which says, what made you take up this innovative turn? Like, why did you change from a conventional mindset? What made you change that? You already explained in your introduction, but what made you decide to pursue a career in?
So to like I would touch base on quickly on the material aspect. So the competing team that we had, the team that we were competing with, they were using biodegradable plastic, which was made out of cornstarch. So they use that for 3D printing, but the problem with that was that is very similar to plastic, which means you have to heat the material before it's deposited, and that changes the time that it is printed and then the shape that it is printed. And so in terms of that specific question, biodegradable plastic or cornstarch based plastic is something that they're exploring for extraterrestrial use cases. But there are several issues with that. Structurally, it has a good compressive load, but laterally it is not so good, as in if you push the structure from the side, there is no layer to layer addition that much in that material. So those are things. And in specific to your question of why this transition, I would like to tie it to one piece of suggestion. Talk to a lot of people, as in for any student, anyone who is interested, talk to a lot of people from different domains. Not just architects, talk to people from finance, talk to people from economics, talk to people who are in medicine field, extremely diverse fields, because they tend to give you a very fresh perspective of what can be done. For example, I wanted to kind of suggest few names. I wanted to add them in the presentation, but I didn't get time to do so. So I will let you know those names physically. So these are the people who kind of inspired me as I came from college. So one was our own junior, Ramesh Balasubramaniam, who is doing his PhD at IIT Madras. So he kind of works on this specific area called non-reconnaissance structural testing. For example, if a structure is in a very dilapidated condition and then you can't enter it and then do all the structural analysis, how would you do that? So he's using machine learning in order to do that, computer vision techniques and things like that. A very simple example to explain his project is that we use these Instagram and Facebook filters, right? And then you see all these mustaches and hats and everything in those filters. So what it is doing is it is basically capturing features of your face and then trying to differentiate, okay, which is a lip, and if it is and they can't write explicit code saying that if it is pink, it is a mouth, and then you put a mustache on top of it, because person to person the color varies. And then if something in your background is pink in color, then it will put a mustache on top of it or a hat on top of it. So you don't want that to happen, right? That's why they use machine learning, so that it gets trained from a lot of different people. Same way, Ramesh is using machine learning in order to kind of this is my understanding, he's doing something much more advanced as well. But base level, he's using photogrammetry and LiDAR based captures of walls and then identifying cracks. And then with those cracks, he's identifying the structural capability of the particular wall. It's the same principle of identifying your facial features by Instagram or Facebook filters, but here it's being used for a different application, which is in the construction field. So these ideas, they tend to pop up only when we talk with multiple diverse fields. And so it's always required to kind of talk to different people and get different perspectives, so that we also know that where we are in the society, and if we do something, and is it going to be impactful and things like that. Because we might have a great idea in our mind, but once you put it out as a business model, or once you put it out on the market, it might not be worth as we think, or something we might think very trivial, but it might be worth very much in the other fields, or when someone else hears about it. So talk to a lot of different people. And I know that I spoke more about technology part, but there are also other career trajectories I have seen people take. So our own junior, another junior, 2 years junior to me, Vishesh Shankar. So he finished his architecture. Most of you guys might know him. He finished his architecture and then he's right now into law. So he's more into policy making and stuff. So he's gaining that expertise and then bringing it to architecture. So the more like we've learned architecture, and then that's the beauty of the field, right? Like we can relate to a lot of other things, which I don't blame engineers, but like our way of thinking is much more like we see a broader picture than like the engineering counterparts. So architecture by itself gives you the beautiful thought process of like, okay, if there is this in this field, I can borrow it and then kind of like use it in my field and then develop it in this way. So that is one. Ramesh Balasubramaniam from IIT Madras, Vishesh Shankar from our college who's doing law, and then there is Varusha Venkatraj who's doing her PhD at Texas A&M. She's doing a PhD in construction management, facility management, and embodied energy. So people who are asking questions about embodied energy or energy management, you should probably reach out to her. If you just go search Varusha Venkatraj in LinkedIn, you should be able to find her profile. You can reach out to her. And there are lots and lots of such people who are around us who are doing a lot of inspiring stuff. So I feel that I'm kind of like fortunate to have kind of like met these people who motivated me to kind of like take these turns.
True. I think you're being too modest here. You can say that you're smarter than the others as well. But otherwise, no, I'm just kidding. But I think you are right in a way where you say that architecture education gives a person an opportunity to explore varied fields, because his mind is already set in a platform of creativity, I would say, where you can explore multiple things. So that's what they say. Architect can, I think there's one article which I read long time ago, which say an architect can do 67 different jobs, avenues that are there. So you are jack of all trades, and so you could explore multiple things. And you're right in a way where you say that connecting with people of different backgrounds, of different interests, would always be a great idea in terms of developing your own ethos as well, like in a way. And in a way, with these webinar series as well, we have been trying to expose you guys, the students, as well to multiple disciplines of architectural practice, and something which is related to architecture as well. But we're trying to expose you guys to alternate systems as well. So I would request you to stay with us throughout the entire duration, where we have multiple speakers coming up. So tomorrow we have another presentation by the legal front of architecture, because we need to understand the legal side of the practice as well. What are the rules, regulations that an architect should already know? So we're getting an expert from the legal front as well. So it'd be great to have you guys tomorrow at 11 o'clock. And this is continuing for the next couple of weeks at least, where next week we have another presentation by landscape architect turned planner from UK. She's a practicing planner in I think reading in UK. So she's going to give us her insights on planning the future and what are the principles of the planning field as well. So stay with us, and I wish, I think we have already gone beyond midnight for Naveen.
I took so much time in presenting. I guess I exceeded the time limit. Sorry about it.
I guess I think it's fine, because we let you sleep now, and then there are quite a few questions similar to what you already answered in terms of materials, in terms of softwares, and how do you move from conventional to an additive kind of system. I think we had Kavita as well a couple of weeks back, who presented on how there's going to be a transformation from a conventional system to an additive constructive system. So it's quite interesting to see you guys in the field and understand, seeing that you guys are exploring multiple avenues. I personally thank you on behalf of Meenakshi as well for accepting the invitation, and I thank all the participants who have logged in early in the morning at 10 o'clock. So I thank you again, and I thank the team, Pavitra ma'am, Gautam sir, Dalaja ma'am, the HOD, the entire family at Meenakshi, for giving us this opportunity to run this webinar series. Hope that you enjoyed the session, and
definitely.
Stay tuned.
And thank you so much again. Thank you to Stanley sir, and especially to Pavitra ma'am, Jalaja ma'am, and to you, Nitesh. I've heard great things from Gautam, that like you kind of like pushed or spearheaded this entire thing. So thanks for actually considering me for this. And just a minor joke. I see a lot of my friends with like weird names who told that I will log in with like a name called Kakakapo and things like that. So it's funny to see all those people here. Thank you guys for staying at a Monday morning. Hope I didn't bore you guys. Romba bore adikala nenachukren. And thanks. And if you have any kind of like suggestions, feedback, jokes, comedies, just reach out to me. Okay.
Perfect. Guys, you can send in your feedbacks. So there's a link on the chat box as well. Feel free to give your feedbacks, your suggestions. We'll make sure that we forward all your positive and negative feedbacks to Naveen as well. So if there are any negative points there, otherwise, see you tomorrow, guys. Take care.
Thank you.
Stay
Thanks.
safe.
Yep. Bye bye.